Hi everyone, welcome to another Hudson and Thames reading group. It's really nice to have another live session. So last week was a public holiday for the team, so Michelle did a really nice recording for us. But this week we're back to being live, which is always exciting. We'll be covering, or at least rather the topic of today is going to be deep reinforcement learning for portfolio allocation, part 1. So this is quite cool in many ways. We'll actually be splitting this up into 2 different parts. The main reason being is we're not just going to be looking at a single paper. We're going to be looking at a range of works put out by Eric, Saltiel and Sandrine Ungari. They've kind of done a very interesting job of introducing a lot of financial practitioners to reinforcement learning. And this is a really kind of interesting approach. And one of the things we'll discuss about a little bit later is why I like this work so much. But a lot of that's got to do with the fact that there has been a really good attempt by the authors to bridge the gap between 2 worlds that don't interact that much. So without further ado, let's get started. So I kind of want to start off this talk by bringing our attention back to the biggest watershed moment in reinforcement learning kind of in recent memory. And that is what happened with AlphaGo. And it's a very key point for me that illustrates why I think we should be taking reinforcement learning seriously and ultimately why reinforcement learning matters. And a lot of you have probably seen this documentary about AlphaGo. It's the first time a machine and essentially a reinforcement learning based algorithm was able to beat the world's #1 player in the game of Go, which was considered for many years unbeatable. I think something like 2+ decades earlier, chess had definitively kind of defeated humans, but Go was considered, just because of its open-ended nature and the number of possible positions, Go was considered a unsolvable problem by artificial intelligence. And then a couple of years ago, it turned out that wasn't the case. But the key thing I kind of want to illustrate about AlphaGo is this quote from the documentary, which is that what surprised me the most was that AlphaGo showed us that moves humans may have thought are creative were actually conventional. I think this will bring a new paradigm to Go. The kind of moves that AlphaGo was making and the kind of strategies that it was employing, they were not typical strategies that you'd see a human do necessarily. They were new kinds of strategies and they were novel. And that in and of itself is extremely interesting. I think a lot of the excitement around reinforcement learning lies in the fact that novel strategies get developed and that novel approaches to old problems kind of naturally come out of trying to solve for this reward function. And this, in my opinion, is why I think reinforcement learning really matters. It allows us to develop new strategies that are unconventional and go against the grain. Okay, so like we alluded to earlier at the introduction of the talk, this is based on multiple resources, but it more or less has the same content. So this talk predominantly focuses on the paper, which is called Bridging the Gap Between Markowitz Planning and Deep Reinforcement Learning. There are also slides and a talk that are based on this. And so to learn more, you can check all of these out or just stay tuned for next week's talk. Again, I mostly want to focus on the paper, specifically because of that bridging the gap that I alluded to. So the paper kind of has a very cool motivation, which is that, financial practitioners and asset managers and portfolio managers, you kind of have this very kind of traditional approach to things. And there's, on the other end of the spectrum, where there's all of these machine learning engineers that are working on the deep reinforcement learning problems, we have all of these algorithms that are in search of a good problem to solve. And kind of marrying these two would be something that is very beneficial to both. I personally really like this paper. It bridged the gap for me, being someone who's actually not financial first. So for those who don't know, I'm actually trained as an engineer. I have a PhD in electrical electronic engineering, and I worked as a kind of machine learning engineer as a consultant for a very long time. And so I think this paper did a fantastic job of kind of bridging that gap from the one end. And having read it, a couple of times, I think it does a really good job of bridging the gap from the financial end as well. So it's a great paper. It's very accessible, which is something that I think should be praised. So let's kind of talk about one of the main premises of the paper, kind of what they talk about, and that's the drawback with traditional methods. So traditional methods based on kind of portfolio optimization, they typically have this one-step optimization where you look at the entire past history and then you kind of allocate your portfolio. It's also backwards looking. So it's not kind of trying to predict the future. It's entirely about looking at what happened in the past. It has some strong assumptions about what risk is and how risk manifests itself and how we measure risk. But the most important kind of key point is that there's no dynamic mapping between the market conditions and the portfolio allocation that takes place, right? The tools are blunt. And kind of if we look at examples, it can illustrate that, right? So between all of these variations and modifications of the Markowitz kind of approach, right? Markowitz, minimum variance, maximum diversification, maximum decorrelation, and risk parity, the problem kind of ends up lying in the maths, right? So sigma here is the covariances of all the various assets. And the problem with a covariance matrix in many ways is what you're asking it to do if you're considering, let's say, two assets, is you're asking to compress an entire history of two assets, right? And how they relate to one another and their relationship. You're trying to compress that down into a single number. And that's quite a lossy thing to do, and it's also a very noisy thing to do. If you watch The Lord of the Rings, or you read The Lord of the Rings, or some kind of other movie that you like, for example, and I asked you to summarize that in a single sentence or in a single word or in a single scene, that's a very difficult thing to do, right? It's a very lossy kind of approach. And this is kind of where I think a lot of the flaws come in, and the same kind of case that the paper makes. You have this massive compression which tries to capture a whole bunch of information into a single kind of number or a single matrix. And this kind of like leads to issues. So let's ask ourselves, why do we maybe think reinforcement learning is a better alternative to this kind of approach? Well, the first is that we can optimize at each time step. So we can dynamically change the decisions that we make based on the current market conditions. That's the first big one. The other thing is that these algorithms don't make any assumptions about risk. So we don't tell it that, you need to watch out for volatility. That's something the agents themselves need to discover and to decide whether that is something that's actually worth paying attention to or not. The only kind of assumptions we have to make is the objective function, right? What reward are we trying to maximize over time? So we don't bake our assumptions into the risk. We bake our assumptions into the number we want to make go up. We can also use additional information. So we're not just limited to kind of what the traditional methods force us to do, which is just look at covariances. We can look at things like market conditions. We can look at things like sentiment. I mean, we can choose. If we decided to, come up with an assumption that maybe the wind in Wall Street blows in a certain direction and that makes people invest in certain assets, we could add that as a feature if we wanted to, and the agent will decide whether it's useful or not. The other thing is also the strategy discovery without any kind of implicit bias or feelings or emotion. This is kind of like what happened with AlphaGo, which is very exciting. And also a key point, and it's a subtle one, but a key point is that with portfolio optimization, we're trying to optimize the weights of the portfolio. But with reinforcement learning, what we're actually trying to do is optimize the decision-making process and the function that allows us to choose the weights of the portfolio. So it's almost like you're taking a step back, right? Rather than optimizing the portfolio itself, you're trying to optimize some kind of mapping function that decides on the portfolio based on inputs. And it's a subtle difference, but it's what allows reinforcement learning to kind of make these dynamic decisions. Okay, so I'm just going to cover reinforcement learning in a nutshell briefly. We did cover this previously in our FinRL talk, which I linked to in the next slide so you can take a look at it. But basically how reinforcement learning works is you have an environment, and this environment describes your state, right? So it's kind of looking at things like the market condition, what your returns are, that kind of thing. And the agent is essentially the model that we're trying to train. And this takes in the state as an input, and it maps that state onto an action. And the way it does that, the function it uses to do this mapping is what's known as the policy. These actions in turn affect the environment, which then generates a reward signal, which we propagate back to the agent. And then that updates the state, which we then also feed into the agent for the next time step. And the entire goal of reinforcement learning is how do we train a good policy function in order to kind of maximize the reward over a long period of time. This is kind of the concept of reinforcement learning in a nutshell. So like I said, we did cover this previously. The talk to check out is the FinRL talk. We cover things like the history of reinforcement learning, some of the big pitfalls and challenges, how the theory works and stuff like that. The talk is freely available, so you can go find it on our YouTube channel and take a look there if you want a more in-depth introduction, kind of accessible way of understanding reinforcement learning. I think we did quite a good job there, but I'm biased. But it's definitely something I think you should go check out if you want to learn more. But this is more or less, how reinforcement learning works in a nutshell. You have an agent that takes an action, it gets a reward signal, and it updates the state. Okay, so let's talk a little bit about the paper in particular. So in their paper, they had one kind of goal. We want to train an agent that plans a hedging strategy for a risky asset. In terms of the agent, the actions it could take is it has to choose the weights across 4 different hedging strategies. That's the one kind of decision it has to make, and then how much to leverage its positions. And then in the environment, we have information. So our state, again, we have information on the 4 hedging strategies. We're looking at the past return and the empirical standard deviation on a sliding window. So that's what the agent gets to see. And in addition to that, we also have contextual information, which gives information on the market conditions. So they have things like features that kind of look at things like risk aversion, the bond equity correlation, credit spreads, equity implied volatility, government bond spreads, US Treasury slope. And they had a whole bunch of these. I think in their follow-up talk, which we'll cover, that over 200 features, which they then filter down using a feature selection process. But that's for next week. But the main thing is we're looking at some of our past performance, some of our information about our previous decisions, and in the current market conditions, right? And some of the market conditions over time as well. And then what's the reward? So the thing we're trying to maximize is the performance of the portfolio, crucially after the entire training period. So unlike some of the other models in financial reinforcement learning that we've looked at, where there are intermediate rewards, in this case, they've given the agent a really difficult challenge, which is, I want you to trade over the whole period, and I'm only going to tell you how well you did right at the end. This isn't typically how I would have done it. So it's quite an interesting approach and a very challenging approach for the agent. But this is kind of how things were set up. And some interesting things about the agent is that in a lot of reinforcement learning problems, the agent would be able to observe the entire state perfectly. But instead, what they do in this paper is they use what's known as a partially observable Markov decision process. So instead of actually observing the perfect state, instead what we do is we look at observations. And I quite like this approach. It's kind of, you can see it as a bit of a regularization approach. But essentially what it does is it allows our agents to act in the realm of uncertainty. So because we know that we're only observing a state rather than actually getting all of the information of the state itself, you kind of have to hedge your bets a little bit and incorporate the concept of, how certain am I that the state is correct? And so how this works is essentially you sample a possible observation, which we get to define, given the true next state and the action that we took currently. And in this case, if I understand the paper correctly, it's not super clear, but I think that their observation is simply a lagged set of the previous states, right? Because if you're let's say you're a asset manager, you typically can't change all of your positions immediately, right? There's a day delay. That's the kind of thing that they discovered, is there's a day delay between choosing you want to update your kind of strategy and when you get a signal back. And so what they do is they incorporate a delay. And it turns out in their talk, not so much this paper, but that delay is quite a big one. It makes it much harder for the agent to react immediately to market conditions. But yeah, so in this case, rather than show you the full history of the state, they say, okay, well, there's a probability that will show you an observation, and the observation contains a lagged reflection of the previous states. And some other things that I think are quite cool about this agent in particular, especially if you've spent a little bit of time in the reinforcement learning world or just in the deep learning world, is they use convolutions. Convolutions are really cool because they have this locality property. I don't want to get too much into them. Convolutions will break your brain if it's the first time you're coming across them. But essentially what convolutions allow you to do in this particular case is accumulate together information over time, right? So if you can see in this diagram over here, how convolution works is essentially you slide a filter over a block of information at a time, and you use that to compute a new value. And what this allows you to do is look both across time in this and one dimension, but also across your features, right? So the typical application for this would be in like pictures. Like if you want to do some kind of image classification, you can look at maybe, say now you have a nose detector, and as you slide that across the image, you can figure out which part of the image has like maybe a person's nose or a person's eye in it, depending on the filter. In this case, what's happening is these filters get slid across time, and it starts maybe identifying things like, oh, this looks like a regime change, or this looks like a bull market or a bear market, that kind of thing. Or maybe this looks like a really good time to short, a certain strategy. And so that's kind of what convolutions get you. What's cool about this that makes their agent also a little bit different is they have multiple inputs and multiple outputs. So we see over here, they kind of have a split network that gets married at some point. They look at the asset states and then also the contextual states. And the reason they have to split these, I suspect, is because of the way convolution works, right? These contextual states have nothing to do with the asset states. And so imagine if you had to slide a window over them, they would overlap. And so they have to split them. And then what's also interesting is they have multiple outputs. So remember, the agent wants to do two things. It wants to predict both the portfolio allocation, but also the amount of leverage. And so there's two outputs that happen. And yeah, the other thing that they do is they also add adversarial noise. So I think they actually add noise to all of their observations. So it's not just lagged observations, they also add noise to them to make it a bit more difficult to kind of figure out what the right thing to do is. And I like this approach of adding in uncertainty as a regularization technique. Okay, so this is how the agent works. We understand how the environment works. What data did they use and what kind of training regime did they use? So their data set consists of daily data for the MSCI World Index and 4 proprietary hedging strategies. The data starts in around 2000 and goes to around 2020. So let's just thumbsuck it as about 20 years worth of data. The hedging strategies, they have 4 of them. So there's a directional hedge, a gap risk hedge, a proxy hedge, and a duration hedge. If you don't know what those mean, don't worry. There's a slide where I'll show you a little bit on how that works. Well, it's not that intuitive. And what was interesting to me is the way they decided to do their kind of analysis is rather than do a traditional train test split, what you often see in reinforcement learning is what's known as a walk forward analysis. But what they've done is what's known as an extending or an anchored walk forward analysis. So what they essentially do is they train on a bunch of data and they make predictions over the next year. And then they then add that test set to the training set for the next kind of time step. And they train all of these and they test them the next year. And then you just repeat that process across the full data set, right? So their initial training was from 2000 to 2006. And then they would do a 1-year test and they just roll that window forward by a year. And then they did a maximum of 500 epochs. So 500 times the entire data set. And they had early stopping as well if the validation metrics didn't improve. Cool. So just a quick side note on walk forward analysis. So the regular walk forward analysis isn't anchored. You'd have, your training set would stay more or less the same size. You'd kind of do this, where what they do is an extending walk forward, which is where they kind of incorporate more and more and more training data. There are pros and cons to both of these approaches. You can imagine these kind of agents in this time would be more sensitive to the current regime that the market is in and be able to react more quickly and more accurately. But they would be less robust to the full history. And obviously the extended walk forward would be the inverse. I know it's difficult to train these things and computationally expensive, but personally, I would have loved to see a comparison between these two approaches to see based on like the size of the window, which one performs better and which one performs worse in which scenarios. I think this would have been interesting, but okay, future work. And then let's look at the hedging strategy zoo. So they have the 4 that they have. So the directional hedge has a strong negative correlation with the market. So on the x-axis, we see the market returns, and on the y-axis, we see strategy returns. Then they have gap risk hedges. So these are supposed to react to extreme sell-offs. We have a rates duration. So the strategies go long on a rates duration. And you can actually see it also has a kind of similar negative correlation with the market. And then we have proxy hedges, which are strategies without an explicit short bias. But basically, this just looks really uncorrelated with the market to me. So those are kind of the 4 hedging strategies that the agent gets to choose how much it wants to allocate to at each time step, in addition to the leverage. Okay, so let's take a look at the results. So no surprises, only because, this is a paper on deep reinforcement learning. Presumably they'd want to show that it works, but deep reinforcement learning gets the best return, Sortino and Sharpe ratio. So we see this over here. Essentially what they've done to look at the results is they've taken the annualized results over the last 2 years. I believe it's annualized for the return, and over the last 5 years. So they look, if 2020 is where we stop, they look 2 years back and then they look 5 years back. We see that deep reinforcement learning, gets the best return, the best Sortino, and the best Sharpe ratio. Risk parity actually does better on maximum drawdown. And then also over the 5-year span, we kind of see a similar story, right? And it's a pretty good Sharpe ratio of 1 over 5 years, 1.02. So I think that's quite interesting. But, and this is where kind of I put my skeptical hat on, right? It's still a bit weird for me that we see the traditional methods do this badly. That was quite a surprise for me to see Markovitz, mean variance, and max diversification do this badly with these extremely large max drawdowns. I mean, if you think you're trying to hedge against a risky asset, it's quite a surprise that your drawdowns are quite large, right? It's not something you'd expect a hedging strategy to do intuitively. And so this was quite a surprise for me. So it basically made me scratch my head a little bit, especially since now I actually want to see what the actual returns would be and the metrics would be for each of the individual hedging strategies over time, right? Just to kind of understand how we could get a result like this. It's quite interesting. And the other kind of critique that I have, but it's not for this paper, it's for, reinforcement learning in this kind of domain in general, is that from the previous talks we've done and from the previous code we've kind of shared and experiments we've run in this reading group, we've seen that these agents can be incredibly stochastic, right? So, and we know that an agent with the same weights, given the same inputs, can make very different decisions. And so I would really, really, really like to know what the variance is on these results for subsequent runs, right? So if you're doing like Markowitz, for example, you're going to get deterministic results out every single time based on the covariances. But for a reinforcement learning agent, you're not guaranteed to get the same output. And so was this particular run a favorable run? Did they take the best out of 100 runs? Did they take the worst out of 100 runs? Did they take the mean? Like, how do you report this actually? And how wide are the variances? If you have, a confidence threshold of the returns and it looks like this, you can't, especially because we're dealing with risk, right? You can't just recommend people use reinforcement learning. You really have to be able to bound, what are the possible returns we could get from an approach like this? And so for me, I think it's, in the literature as a whole, it's quite surprising and quite a shame that we don't kind of get to see these variances and deviations on how accurate are these actual models, like how variable are they and how volatile are they actually over time. I think it's really important that we report these. And I mean, this is different for something like large language models. I know when you do an assessment on a large language model, for example, and you're doing, say, a asking question and answering challenge, you don't rerun it multiple times, but maybe we should, because there's a stochasticity there as well. And I think if I had to give one critique of the industry right now, is we need to move towards kind of giving actual bands on what these returns could possibly be, especially if you want people who are risk averse, who are looking at risk to kind of implement these things. But it's not a knock on the paper, right? It's a knock on a lot of the literature in this space. And what I really like about this paper and what I commend the authors on is they've actually published this, which shows you the allocations across time that each of the portfolios actually, each of the kind of strategies took. I think this is very interesting, but it makes me go, which is why we should get someone with an H in their name to join Hudson and Tim, so we can quite literally have everyone just go together. But basically, what's really interesting for me is how the deep reinforcement learning agent goes all in on the duration hedge and then flips to favoring the proxy hedge. There is an interesting deallocation moment, which will look where the agent actually deallocates leverage when it comes into a credit crisis. But this makes me a bit skeptical, right? For a couple of reasons. One, is it always optimal to be maximally leveraged? I don't know that much about this. So Michal, maybe like afterwards you can give some kind of insight whether it makes sense. But I kind of wonder is whether this model was actually punished or for being maximally leveraged. Like, were costs taken into account for having, a margin account, that kind of thing. And because it's quite weird to just think the agent would just choose to maximally leverage, especially if your reward function was just the returns. It's like, okay, let me just be as risky as possible. So it's quite an interesting kind of result. And I would also personally not have anticipated an agent to go all in on a particular strategy for so long, right? If you say to the agent, you don't have to allocate 100% in each strategy at each time step. Instead, what you're saying to it is, hey, you can just balance these depending on what you think makes the most sense. And then the agent chooses to just go all in on one strategy. That's quite an interesting thing to do. It definitely took me by surprise. And so I think this could be an artifact of the reward being maximizing returns. In future work, they actually look at things like the Sharpe ratio and Sortino ratio, which I think is probably a better metric to use. But I also think this could be an artifact of having that very long, extended kind of training, a walk forward analysis. Because maybe, at the beginning of that set, during a certain market conditions, going into this duration hedge gave you all of these results, like all of these amazing returns. And now you're biased by that history where it doesn't make sense anymore. So it's quite a weird one for me. What is also interesting is, and what I really enjoyed is actually looking at the other ones like the Markovits, the mean variance, the max diversification. So of the traditional methods, maximum decorrelation risk parity did the best. If I quickly go back here, we can see they actually did really well, comparatively speaking. And what's interesting is they look the most similar, go figure, and they're also quite balanced, which is crazy why then, the reinforcement learning algorithm just went all in. Very interesting kind of results. And I'm glad this was shown. This is a very cool way of trying to understand how the agent actually works. Okay, and in terms of the deallocation moment that we spoke about, so there's this, you can see it just here, there's this sliver right here that takes place in 2020. And what happens is for a very brief moment, I think this is caused by responses to COVID, if I remember correctly. We see this very brief moment where we switch away from investing in the proxy hedge. And we also I think, like if you can see this is below 100%, we move to actually holding cash. But we deleverage completely for this brief moment. And I think I also suspect that happens at this little dip here, which is a very interesting observation. It's almost like this agent understood, okay, right now is the time to actually deleverage and maybe hold onto a little bit of cash. And that's something that you won't see the traditional methods do. And so I thought this is like where there's smoke, there's fire potentially, while, this part is still, it makes me a little bit, I want to understand a bit more. This is like a flash of brilliance and a flash of insight and something cool and something I find very interesting. So yeah, something worth paying attention to. Okay, so in conclusion, I think, as we've seen now, and as we've also seen in previous talks that we've done, I think this is probably like our third or fourth talk on reinforcement learning. Reinforcement learning is super cool and interesting for finance for a whole bunch of reasons. The ones that I really think makes it cool is the environment is very well defined and we have lots of data, right? Finance is a very data heavy industry, which is perfect for reinforcement learning. The actions you can take are very well defined. They're also automatable, right? So, you can have an interactive broker, you can execute trades, that kind of thing. And reward functions are well defined. We have lots of really good metrics for deciding on whether a portfolio has performed well or performed poorly. And so this is the perfect kind of world to train these reinforcement learning agents. And also, I just think you're operating in a world that favors novel strategies, right? And so this is where reinforcement learning is particularly well suited for strategy discovery. And so I think this is really cool, and why I still believe, reinforcement learning is a really good match for the finance world. And also, reinforcement learning, as we've seen again, it addresses a lot of the shortfalls of traditional methods, mostly just by being dynamic, right? In this particular paper, I think the results indicate that the reinforcement learning does seem to work, but I do really want a more robust analysis on results, not just, in this paper, but also across, all of the literature. I think we have to stop pretending that these things aren't stochastic when they are, and try and see, an amazing innovation would be able to try and get a more deterministic kind of reinforcement learning agent that isn't overtrained. That's a tricky thing to do. So I want to see us kind of do a bit more thorough experimentation with this kind of knowing about the stochasticity. And that being said, subsequent works by the authors have very interesting results and a lot more exciting scenarios where we do see the agents do very interesting things. And I think this is a combination of a bunch of kind of innovations that they've added in. So they do feature engineering and some boosting to kind of make the deep reinforcement learning agents perform better with some clever kind of features that they develop. And augmenting their state with useful features. They also have more interesting actions that can take place, and they have a wider portfolio with more assets. And I'm going to cover this in part 2 next week. So if you're interested in kind of seeing how we can go from this to something a bit more sophisticated and very, very interesting, I recommend tuning in for that. And also, I think it's really important to conclude that there is so much to do with reinforcement learning in finance still. It's very clear to me that we are barely scratching the surface. We have something that we think is interesting and that is promising, but there's so many more questions that we kind of need to answer on these. Like, what kind of data sets can we use? What kind of features do we typically see leads to big results? Because there's no consensus on what we should actually be feeding into the environment. What noise should we be adding? How should we incorporate uncertainty? What kind of rewards should we be using? All of these are open questions that I think, with just a little bit of patience and a bit of research and a bit of putting our heads down and collaborating with some people, I think is going to be a a field where we see a lot of progress in, and I'd like to see more of it personally. And I'm up for it. So get in touch if this is something you're interested in doing. And then just finally, I kind of want to take us back to this. I think it's important to understand why, despite this being a field very much in its infancy, especially, a little bit on the back burner, given that large language models are kind of occupying the spotlight at the moment, is that we're seeing reinforcement learning agents when they're applied in interesting scenarios, is we're seeing them come up with strategies and make moves that make human strategies and human decision-making appear conventional. This is a very kind of key point that I kind of want to hammer home, and which is why I think we should keep looking at this. I don't think it'll be too long before people start bringing out really excellent tools in this domain, and it's something we should all be paying attention to. Even if it doesn't mean it will replace people, at least inform strategies, come up with new ideas, provide some kind of inspiration. I think that's ultimately where this will be going. And I personally anticipate that the momentum will swing back to reinforcement learning over the next couple of years. Although, to be fair, we've actually seen papers come out that show that large language models can approximate reinforcement learning with the right prompt. So who knows? But I do think this is going to be a active field of study and intrigue in the future. And so that's why I still really do believe reinforcement learning matters. All right, perfect. So that's basically the talk. So yeah, thanks for joining.